Welcome to our class in research. So we're going to look at estimation and sampling. So in quantitative research, estimation and sampling are the fundamental processes that we use to make inferences about a population without studying every member. Okay, so we are going to use as a foundation for our class in hypothesis testing. So you need to pay particular attention, especially in the concepts that we are going to have in here. So what is an estimate? What is a sample? So we'll learn how that sampling allows the researcher to select a subset of a population, while estimation will use that um, sample data to make informed judgments about a population parameter. So when you're dealing with a population parameter, we're dealing with the entire space, and the sample is a subset of this population. Okay. So sampling by nature is simply the process of selecting what? A subset of individuals or items from this larger population, which we call the population. So what is a population? A population includes all these observations that are in there, right? So the group of individuals that are joining this class are just a sample of the population from the entire GBS 541 class. So the population includes all observations, like all students in the class. A subset is simply a segment of the entire population. So what is a statistic and what is a population parameter? A parameter is simply a numeric characteristics of the population, and the statistic is a characteristic that is computed from a sample. So what is the role of sampling? Why do we sample instead of conducting the entire census? The entire population, we call it a census. Okay. Then a population parameter, if we're sampling a small population parameter, that is a sample. So it's important to conduct sampling because it's cost effective. So studying a small sample is cheaper than surveying the entire population. It's time consuming because it reduces the time required to collect the data. It is accurate because if it's done scientifically, sampling will provide results that are nearly as accurate as the census. It is feasible. Some populations like hospital patients or industrial machines are too large or inaccessible. So no matter how much money you may have, no matter how uh, much time you may have, you may not have sufficient population. You may not have sufficient or accurate information to know how many babies are born in a day. So feasibility or sufficiency of I can call it the universe size, right? So that's why we do sampling. Now we're going to look at the formulas for sampling. We have sample size is equal to um, z squared, s squared over a squared. This is the sample size formula. And we also have the sample size formula, z squared, pq over e squared. All right. So these are the formulas for sample size. And an estimation, an estimator, formula for a confidence interval is simply the mean plus minus z, standard deviation over n. And the sum that I need you to know is that we have three common confidence levels. Okay. So we have confidence levels, significance levels, All right, so look at this table in mustard. Okay, so we have confidence levels. We have 99. Okay, we have 98%. We have 95%. We have also 90%. So these are the confidence levels. The difference from 100 is called the significance level. So 99 minus 100 minus 99 is 1%. 98 from 100, 2%. 95 from 100, 5%. And 90 from 100 is 10%. So when you divide this by 100, we call it alpha. So here you have 0.01. Can you help me for 98%? What is the alpha?
0.02.
0.02, Then 95%,
0.05.
0.05, Then 10%,
0.1.
0.10, correct. Okay. So now, with that being the case, I want to teach you how we can read these from the tables. How we can read the Z values without memorizing them, in case you're given any other percentages. So today we're learning about the normal distribution tables. To say we are able to read these normal distribution tables from inside and from outside. Okay, so I hope you remember how these tables are read. Just being some statistical tables and the Z tables. Statistical. So the normal distribution tables. Okay, so you can see the table. So we understand that reading can be in two ways. So you read from the horizontal to the inside here. So we say the reading for a normal distribution table, for instance, if you have 1.25, you go under 1.2 and 0.05. So this one, the last number is read from the top. So 1.2 is here and 0.05 is there. So where they meet, this is what? 1.25. This is a reading for 0.8944. Okay. So give me what is the reading for 1.96. Where do you go?
1.6 and 0.06.
1.9
Oh, sorry, 1.9, my bad.
and 0.06. Okay, is that clear? So this is where the reading is. Are we all together? Now, if I
Yes, sir.
to give me the reading of Z from inside, so 0.975. This is a Z. Give me this is the probability. Give me the Z. You just add 1.96 and 0.06. Okay, so it gives us 1.96. So you give me the Z for 0.9525. What is Z of this probability? 0.9525.
1.67.
So you went here, 1.6 and 0.07. Are we together? 1.67. Is that clear?
Yes, sir.
Okay. So that is how we okay. Okay. So we can now go to another random figure. So if you want to read these figures that you're seeing here, okay, the first step is simply to find 1 minus alpha over 2. Then you read it from inside the table. So let's try to read for 95%. What is the alpha for 95%? What is alpha for 95%? 0.05, right? What is alpha for 95%? I hope you know the alpha. 99% is 1%, so 0.01. 98 is 2%, is 0.02, the alpha. 95% is 0.05, which is alpha. 90% is 10%, which is 0.10. So what is the alpha for 95%? 0. What? 0.05, isn't it? So this is a formula. So when you compute that, what are you going to get? 1 minus 0.05 over 2. What answer do we get? 0.9750. Is that what you're getting? Is that what you're getting?
Yes, sir. 0.975.
Yes, so you go inside the table. Which one is 0.959750? It is here, 1.96. Okay, that's 1.95%. We can say the Z for 95% is what? 1.96. Okay. So for 90%, who can guess? How do we find the Z for 90%? 90% is what? 10% or 0.10. So you do 1 minus 0.10 over 2. What do we get?
0.95.
0.95, correct. And in the morning, we try to look at the reading for 0.95 from inside the table, that it is equidistant between two. So 0.95 is either one can say it's this one, the other one can argue this one. Okay? So this one is below by 5 points, this one is above by 5 points. So you pick the smallest one and add a 5 there. So it's 1.645. 1.64, then just add a 5 there, meaning it's exactly in between these two. That is where the 1.645 is coming from. Okay. If you don't find the exact one, you go to the closest possible. Okay, let's try 98%. Who wants to try 98%? What do we do?
It is 0.99.
1 minus 2% is 0.02, all right, over 2, which will give us 0. What? 0.99. 0.990. So that's clear.
Yes, sir.
So let's look at what is the reading now for 0.9900.
It will be 2.32, between 2.32 and 2.3.
Which one is the closest? 2.33. Right? Do you agree?
Yes.
Right. So this is, now you know how to read it on your own. So this is 2.33. If you do the same for 99%, you find it on 2.58 or 2.575. Right. So these are the Z figures. Okay. So now with these Z figures, you now need to understand how to calculate the sample size and the confidence level. So suppose now you know 99% the Z is 2.575. 98%, which is the same as 2% or 0.02, the Z is 2.33. Okay. So quickly, can you remember what is the Z for 99? 2.575. 98, 2.33. 95, 1.96. 90, 1.645. Is that clear?
Yes, sir.
So sometimes you'll say that find the 95% confidence interval. Find a 95% confidence interval for a mean of what? For a mean of 10 departure. The sample size is 36 and also the standard deviation is 12. What is our 95% confidence interval? So confidence interval has been given by the formula mean plus minus Z over standard deviation over N. So what is our mean? 10. We put 10 there. Then what is our Z? Our Z at 95% is 1.96. We've already established from here. 1.96. And what is our standard deviation? Of. And what is our N? 36. By the way, we use Z when our sample size is more than 30. So here our standard error, root of 36 is 6. 6 into 12 is 2. So here we're going to have what? 10 plus minus 1.96 times 2. All right. So the standard error is given by standard deviation over root of N. When we apply these two, we call it the margin of error. So what is the margin of error? The margin of error is when we apply 1.96 times 2. Of course, you'll not be asked to define it, just want you to know it. So this is what? 3.92. When you subtract, we get 6.08. When you add, we get 13.92. Okay. So this is what we call the confidence interval. All right. All together. Confidence interval. All right. Right. So let's find an 98% confidence interval for a sample size of 100 with the standard deviation of 20. And the mean is 15. Want to try? So using that, our mean is 15. Our Z at 98% is what? 2.33. And our standard deviation is what? 20 over square root of n. Our n is 100. So standard error, square root of 100 is 10. 10 into 20 is 2. So we're going to have 15 plus minus what? Standard error, 2.33 with the 2 here. So what do we have here? 15 plus minus 4.66. So we subtract to get the lower bound and we add to get the upper bound. Is that clear?
Yes.
So confidence interval for a proportion is slightly different, but the key thing you need to master the what? The Z values. So proportion is given by Z PQ over N. Capital N. The proportion, suppose you're given as 20% and you're given your N as 100. And we're given that our alpha is 0.01. What is our confidence interval? So our alpha 0.01 means that our QM is what? What is our Z? So if our proportion is 20%, 0.2, meaning the remainder should be our Q. They should add up to 100. So if our P is 20%, what is our Q? 100, 80. Then this 0.01 will give us our Z, which is 2.33. Then PQ, our P in this case is what? 20%, 0.2. Our Q is 80%, 0.8. And our N is what? 100. Okay, right together. But this is something complex. Huh? So if you have your computation properly, you subtract the proportion lower bound and the upper bound you add. So this can also take us to calculating our sample size. Suppose we have the following, okay? Are we together so far?
Yes, sir.
Hey, anyone behind?
Maybe clarity on the Q.
Q is simply like significance level and confidence level. So if your P is 10%, your Q would be 90%. Okay. So
Thank you, sir. Thank you.
those things you must understand. So let's look at these another example. So suppose you're given the following question. Suppose you're given following question. Find the sample size of a proportion and of a normal sample. So here a researcher wants to estimate what? The mean income of nurses in Osaka. From pilot study, the standard deviation is 1,200 and determine the sample size if the researcher wants to be within 200 at 95%. So 95%, our Z is what? 1.96. So we're going to use this formula. What is our Z? 1.96 squared. And what is our standard deviation? Estimated standard deviation is 1,200. So 1,200 there, squared, over our error. Error comes in the term within 200. So we put 200 there. Okay, squared. All together. So we calculate our sample size formula there. Okay. Then I go to our next question. Next question here is an economist wishes to estimate the proportion of households that own a smartphone. Plans to be 95% confident that the proportion will be within plus minus 5 of true mean. From previous surveys, it is believed that 60% of the households own smartphones. Determine the sample size required. So what is our Z at 95%? 1.96. So we put 1.96 squared. Okay, then our proportion. Okay, 60%. So 0.6, meaning our Q is 1 minus P in short. So 1 minus 6, 0.6 is what? 0.4. That's where the difference is, you can see, eh? Then our error is plus minus 5%, so here 0.05, since it's a percentage. Okay, are we following? So if they gave us 98%, what would be our Z? If they put 98% here, what would be our Z? If this was 98%, our Z would be what? 2.33. If it was 99%, our Z would be what? 2 point what? 757. Okay. 2.558 or 575. If it was 90%, 1.645 from our song. Okay. What if it was 95? So 1.96, as has been shown here. Are we together? Are we following?
Yes, it's clear now.
Yeah. I'm trying to simplify this jargon. I'm talking about a lot of things here that you must not forget to remember. So I'll send these questions as your homework, but I just want to give you the solutions so that as you do them, you understand. So a sample of 25 students has a mean of 75, standard deviation of 10. The researcher wants to estimate the true score of margin of error at 4 and 5%. Compute the sample size. Okay, what is the sample size? Then how will sample size change? The desired margin of error was 2 instead of 4. So here you are estimating what? The changes in error. How does it affect sample size? So here what formula do we use? Not the proportion formula, but the z squared a squared over what? E squared. What is our z? And 5%, that's 1.96, right? What is our standard deviation? It's 10. Sometimes we're given the variance 100, you square root it, then you square it. Okay? So, or you don't square that, or you put it as it is. Because standard deviation squared is the variance. Then our error is what? 4. You calculate sample size. Then part B, if we change the 4 to 2, what will be the effect on sample size? All right. Then we are told that the Ministry of Health is conducting a national survey to estimate the number of hospital visits per year. This standard deviation 2.4 from the studies, and the desired margin of error is 0.4 visits. With a confidence level of 99%, calculate the minimum sample size required. Use Z 0.005. We know that at 99%, our Z is what? 2.575 or 76. This should master now. So what sample size are we using? So Z squared, A squared, E squared. So our Z has been given there, 2.575. We're given a 76 there. Our standard deviation is what? 2.4 squared. And our error is what? 0.4. Carry together. The square, don't forget the square. Are we understanding the way the application
Yes, sir.
is coming? Okay. Right. So this is what is happening. So we'll continue tomorrow. We'll end here. I'll send you homework based on what has been done. Thank you so much for your time. Have a good night.